Okay, welcome everybody. I'm happy to introduce Andrew Rollins from NOAA. Title of his talk is up on the screen there. So Andrew got his BS degree from Harvey Mudd College in physics. And then he went to UC Berkeley and worked with Ron Cohen with NOx and different nitrogen species, looking at the impact on SOA. And then in 2010, he came to NOAA to work with Dave Fahey, first working with water vapor in the UTLS region, and for the last several years, he's been working on SO2 in the same UTLS region. So anyway, I'll turn it over to Andrew.
Thanks. All right. Well, I'm going to talk today here about what I've been working on the past few years, which is trying to make accurate measurements of SO2 in the upper troposphere and lower stratosphere. This has been a question that people have been wondering about for decades, I guess, about really how much is there, and it's important because it impacts the aerosol budget for the stratosphere. Here's a brief outline of my talk here. I'm going to try to talk a little bit about just the history of stratospheric aerosol research and what's got us to where we are, and then tell you about the measurements that we made on this aircraft. This is the B-57, which we've used for 2 different missions, and I'll talk about what I'd like to do in the future with some of these data, and hopefully involve some more people in this room. All right, so stratospheric aerosols. This is a picture of the stratosphere in post-Pinatubo, and you can see there's this big fat layer of aerosol up here, which makes it easy to see and makes a nice photo. But even in the absence of these big volcanic eruptions, there's still aerosol in the stratosphere all the time that comes from basically primarily from species that come from the surface and then make it up into the stratosphere, and either aerosols that are transported into the stratosphere or species that are oxidized there and then condensed to make aerosols. And so these guys, of course, are important for radiation, just like the ones in the troposphere are, but one distinguishing characteristic is, since there's no clouds in the stratosphere, to remove them, they're basically removed by a large-scale circulation, which gives them a lifetime of a couple of years instead of a week, like the aerosols in the troposphere. And so they have maybe 2 orders of magnitude longer lifetime than ones that are in the troposphere, and this means small sources of these things are important for climate. One estimate from a recent paper, this is Peng-Fei's paper, is basically something like 20% of the anthropogenic aerosol radiative impact is due to particles in the stratosphere. So that's pretty significant. And then the other thing that's important about aerosols in the stratosphere is that they impact ozone. So particles up there can catalyze heterogeneous reactions on their surfaces, which can destroy ozone. And we care about that. So let's see. So a lot of what we know about these aerosols in the stratosphere comes from what's happened from volcanic eruptions, both large ones and small ones. This is a figure from Susan Solomon's paper in 2011. And the point of this paper was actually to look at the recent trend in radiative forcing, and noted that, at this time there was this discussion about the hiatus and all this, but the question is why the planet hasn't really gotten as warm as we might have expected based on all the greenhouse gas emissions. And she pointed out that about 25% of the 25% of the increase in greenhouse gas warming that would have occurred since 2000 was offset by an increase in stratospheric aerosols, and this is now known to be due to small volcanic eruptions. But we also know these large volcanic eruptions also create these big increase in stratospheric albedo quite a bit and have impact on the surface temperature for a couple of years. And then this is showing some of what's been learned from the Pinatubo eruption on ozone in mid-latitudes. So you put these aerosols, a significant amount of them, in the stratosphere where the ozone is, and they catalyze a couple of reactions that basically shift the NOI and chlorine partitioning, and this can destroy a significant amount of ozone. So these are measurements of NOx and NOI and CLO and CLY on the ER2, showing before and after Pinatubo, and there's a shift in this partitioning. And then some measurements of ozone show that there's a significant destruction of ozone there due to these aerosols. So this isn't something that, this is really a Pinatubo thing. But small amounts of aerosol, we think this is basically, this destruction rate is somewhat linear in the aerosol surface area. So small amounts of aerosol up there also can do this. And increasing it might destroy some ozone. And so one of the reasons we're kind of interested in this now, a lot of people are thinking about this, is there's a lot of discussion about possibly enhancing stratospheric aerosol intentionally to offset the increase in greenhouse gas emissions that doesn't appear to really have an end. So a couple major reports from societies, from the Royal Society in 2009 and from National Academy in 2015, basically say that this is research people should be doing, is thinking about, do we understand this system well enough that we could predict how much, can we predict what would happen if we put a bunch of SO2 in the stratosphere or some other species to try to offset warming? And there are a number of people in this room, obviously they're spending a lot of time thinking about this, doing various scenarios of, it comes down to how well do we understand circulation in the stratosphere, how well do we understand the SO2 oxidation kinetics and particle formation and whatnot. So, all right, so I'm just going to kind of go into a brief history of what we know about these particles. And this kind of starts in the 60s, where this paper here, these guys made measurements of aerosol on balloons, both using optical particle counters and impactors, and found that if you look well above the tropopause, there's kind of a layer here where the mass mixing ratio of aerosol is maximized. And the impactor measurements of these particles suggested that most of this stuff was sulfate. And so the question was, how can we explain this? And at the time, one of the confounding factors was reduction circulation wasn't really widely accepted. And so you had to explain this by diffusion of trace gases up into the stratosphere. And he suggested that this could be due to either possibly SO2 or H2S diffusion into the stratosphere and then oxidation there to form these particles. And apparently for quite a while there was a discussion actually about what the SO2 plus OH reaction rate coefficient was at these cold temperatures and low concentrations of water. And this was I guess an active field of research for about a decade, and this was very important for understanding whether or not you could explain this layer due to that oxidation of SO2. Eventually, he published another paper. This is in '74, and says that if you have 100 ppt of SO2 at the tropopause diffusing up into the stratosphere, that could possibly explain this layer. And then in '75, carbonyl sulfide was first observed in the atmosphere, and shortly thereafter, Paul Crutzen wrote this paper saying that this is probably a better explanation for this layer. And this is still believed to be the case. It's pretty straightforward. Basically, the OCS, this one on the right here, this shows the OCS oxidation rate. OCS is basically only destroyed in the stratosphere primarily by photolysis, and it's not destroyed in the troposphere at all. So this is sort of a maximum in the OCS destruction rate of about 25 kilometers, and that coincides with this maximum in the stratospheric aerosol mixing ratio that you see. And we have good measurements of OCS. There's some in-situ measurements, and then these are measurements from ACE FTS. It can do a good job and shows you that up very high in the stratosphere there's not much, and around 25 kilometers is sort of where the maximum destruction rate is. So OCS is still believed to be really why there is a maximum in the mass mixing ratio of aerosol, say 25 kilometers in the tropics. But it doesn't explain all the aerosol in the stratosphere. So around the same time, there's been measurements on, this shows a time series starting in the 70s. This is optical particle counters on balloons. This is primarily from Wyoming. And then up here are some LiDAR measurements. And basically what these records show you is a couple things, that these big features that you see in the time series coincide with these volcanoes that have happened. And that's because the volcanoes are known to put a significant amount of SO2 in the stratosphere. And then from these time series, you can derive sort of how long does it take for these particles to get flushed out. yeah, so the volcanoes explain these big features. But a question in the sort of arose in the 90s, I guess, first. Well, that's the first I'm aware of it, is from this paper by Hoffman. He was looking at basically, if you look at, after these large volcanic eruptions, the aerosol decays to what might appear to be a background value, and before and after some of these volcanoes, and there's possibly an apparent trend upwards in this extinction in the stratosphere. And it was proposed that this could be due to possibly aircraft emissions of SO2. And then again, this is a paper in 2009, this question arose. This shows measurements of stratospheric aerosol optical depth using LiDAR at Mauna Loa, and appears that there's sort of an upward trend in this time period also. And it was thought this could be due to increased coal burning, primarily in China. So this shows the time series of coal consumption, and then there's this big uptick in the early 21st century. So that was kind of, those people were trying to understand what's causing these trends, and really, are these trends real? And so then the other thing that's been, I guess, in the last decade really is thinking about specifically how important are sort of unusual transport situations to get possibly short-lived pollutants up into the stratosphere where they might be oxidized to make aerosols. And so this shows a figure from Bill Randall's paper in 2010, and there he showed that you can see that this is using ACE-FTS measurements of HCN. You can see that the monsoon really does bring a lot of material out there that's short-lived, and HCN was used because it's a good signal on the satellite, but there are a lot of other things that could be brought up also that they can't be measured that way. So there's this question of how important is the Asian monsoon for transporting all kinds of stuff into the stratosphere. That's definitely an ongoing question. And then also something that was sort of brought up again in the last decade is this question of how important is transport sort of in the Western Pacific. So in this region, there's the ozone there is very low near the surface. It's very clean, and there's a lot of convection there. And because the ozone is low, there's not believed to be a lot of OH in the column there, and so it's thought that you could potentially have short-lived species, possibly that would come from Asia, and get wrapped up and convected into the lower stratosphere in this region. This one's out of a paper by Marcus Rex in 2014, and he showed here that, for example, generally in the troposphere, the lifetime of SO2 might be something like 5 days, but inside this region, it's more like 18 days. So where it's kind of gone in the last decade, I guess, or even before that, is using global simulations to try to get at the details of the stratospheric aerosol budget. And this is a figure that was published in this Spark report in 2006. And the conclusion from this report, or one, was that, well, we don't really know how much SO2 is at the tropopause, because there just hadn't been any aircraft measurements of it there. But if there is 40 ppt is kind of what they used, then you could have SO2, just the flux of SO2 up into the stratosphere, be as important or almost as important as OCS for forming stratospheric aerosols. And then again in 2015, this is a similar figure that tries to get at the budget of stratospheric aerosol using the Sokol AER model. And this model actually didn't prescribe SO2 at the tropopause, but used known emissions sources at the surface and other chemistry in the troposphere that generates SO2. And with this model, they still end up calculating about 30 or 40 ppt at the tropopause. And that's shown over in this figure here. This is a profile, one of the figures out of this paper. It shows the profiles they have in the model of SO2 from some different seasons and different colors. And then these dashed lines show these retrievals from the MIPAS satellite, which had become available just a couple years earlier. And what the MIPAS satellite observation showed is something similar to what they calculate in this model, which is there's something around 30 or 40 ppt of SO2 at the tropopause. And if there's really that much there, then that would mean SO2 was about as important as OCS is for forming stratospheric aerosols in the absence of these big volcanic eruptions. Okay, so this is kind of where our research starts, is basically to try to go make some measurements in this region and find out how much is there, find out what we can learn about the accuracy of the models in these satellites. So we developed this instrument that uses laser-induced fluorescence to measure SO2. And so what we do is we have an optical cell that is inside the aircraft, and we sample air into it, sample air through it, really. And in there we have a tunable UV laser that just passes through the cell. And the SO2, if it's in there, will absorb some of these laser photons and emit redshifted photons that we can count, and then we just calibrate that thing. So in this kind of a laser-induced fluorescence experiment, the signal you get is proportional to the absorption cross-section for SO2 and the fluorescence quantum efficiency of the molecule. And so this shows a spectrum that we can acquire with the instrument if we just scan the laser. So this is pretty high resolution. So this is 216.9 nanometers, or this is 216.9 nanometers, but this whole scan is, it's like 20 picometers wide is the range of the scan. And in red, this shows the absorption cross-section you can find for SO2 in the literature. And then these lines show the fluorescence spectrum that we can see with our instrument. So you can see we think we're resolving the Doppler limited spectrum. And that's nice because what we can do that is when we normally operate it, we don't scan it. We take this laser and we just tune it on and off of a resonance quite quickly back and forth. And we use that as the SO2 signal, and we can calibrate that using just a bottle of SO2. So we can basically make measurements at about 10 hertz if there's enough SO2 around, say 50 or 100 ppt. At low concentrations, we have a noise level of about 2 ppt. And so we typically average for, say, 10 seconds or something in UTLS, and then we can see the structure there. And the accuracy is about 10%. So I've got a few photos here of our instruments. We've done these three campaigns. First two are on the B-57. This is where it first flew. And on the B-57, we build it into this pallet. This goes underneath the plane. This is a picture of the SO2 instrument with its cover off. And this loads up into the bottom of the aircraft, and then we sample gas through a little inlet there. So it's not that, this is the size of the instrument. And then we flew it there for 2 missions, 2015 and 2016. And this past summer, we took it and integrated it on the Global Hawk. And that's this box up here. So you can get an idea for the size of this thing. And it's not that small, but what we're doing right now is we're constructing a smaller one that can go into a rack. So we're planning on flying this in this last ATOM mission. And this one takes up, in total, about 20 inches of rack space. This is like 2/5 of a G5 rack. So this could be a good instrument for people to want to use in the future if they're interested in doing G5 campaigns and measuring SO2. So these are the flight tracks from our B-57 missions. Our first mission in 2015, we just did these flights out of Houston and tried to fly. A lot of the time, we just flew south as much as we could and did a couple of flights over Mexico. We happened to be on this. These were sort of piggyback flights on a hurricane mission, and so they had an agreement with Mexico. I guess Mexico's happy to have the plane fly over Mexico to do hurricane research. So we were able to fly over there and fly over a hurricane there. And then we did some flights here in the Bay of Campeche and down here, and then one flight north as far as we could. That was fall of 2015, and then in 2016 we took the plane to Guam and we did a series of flights there. And that's a nice place to be because of all this convection and the low ozone that I mentioned earlier. And so it's interesting to learn about how much is there. And and so during 2016 we had a larger suite of instrumentation than in 2015. 2015 was us. We had SO2 and water vapor and ozone, and then Sue and Ellie did some measurements of WAS from these same flights, and that was the whole payload. And then in 2016 we also had some UCAS measurements and aerosol size distribution measurements. So these data they're basically available on the NASA server if anybody's interested in them. All right, and then 17 we did these flights on the Global Hawk, and these ones, Global Hawk's nice because it flies for about 24 hours when it flies. These ones are also piggybacking on a hurricane mission, and we had basically no control over where the plane went whatsoever. And so we got a lot of statistics in the lower stratosphere, but basically the plane would just like cruise climb. So it would go up to about 17 to 18 kilometers really fast, and then just basically climb slowly as the fuel burned throughout the flight. So we don't really have much data at all near the tropopause, but we have a lot of data in the lower stratosphere. So I'm not going to talk about those quite as much, but I'll say a couple things at the end about them. So the questions we've been trying to get out with these data are how much SO2 is typically at the tropopause, and how much might bypass this region and the stratosphere through some unusual events. So sometimes we see big plumes of SO2, and the question is, are those guys important or not? Or can we say at this point? All right, so here are all the data from these two WB-57 missions. And all these dots are individual measurements. And then I've just shown statistics here for these two different missions. And so you can see there's a wide range. This goes from half a ppt up to 100 ppt. And we see a number of times we'll see values up to close to 100 ppt. They're kind of unusual, but we do see some plumes up there. And some of these are actually really appear to be almost in the lower stratosphere, some plumes. But for the most part, it's a pretty dense population at or below 10 ppt. So the plotted here, the median and interquartile range are showed in these red bars here, and then blue is the mean. And you can see the mean's a little bit higher due to these high values. But the median, so for these flights we did in the Western Pacific, the median value is about 5 ppt at 17 kilometers, which was typically where the tropopause was. And then this first mission we did, we saw some higher values, the statistics are higher, so we see about 11 ppt is the median, and the mean is about 14 ppt. So I should say on both of these missions, really, we used this GEOS5 forecast model to intentionally try to go sample some high SO2 events that were predicted due to convection, bringing SO2 from volcanoes mostly up into the upper troposphere. And we succeeded in sampling some of those. So we know some of these high values that we saw on these flights were due to these volcanoes, and same here. And that's that's why we think this distribution is basically higher than the one we saw this year, is because there's just a larger amount of data at these plumes that we did sample intentionally. So it's worth keeping in mind. I guess we think that, we assume that we would have, on average, probably seen a little bit less if we'd just flown everywhere without targeting these plumes. I made this is just a zonal mean distribution from just these data from this first mission. You can see it. There's not a lot of data, but you can see this goes from 10 degrees north to 50 degrees north. We did this one flight north and dive, and even just the small amount of data, I think, kind of shows something that we probably kind of expected to see, which is in the below the tropopause we see lowish values, but up in the stratosphere we see just a few ppt everywhere or below. And then with these data, that year, I think that the jet stream was kind of a little bit farther north than typical. So we did an analysis where we used basically the data up to 25 kilometers or 25 degrees north, and used that to sort of represent the tropics. And I'm showing that here in right. This shows the temperature measurements at different latitudes and the ozone. And you can see up to about 25 degrees north, the air looked pretty tropical. So we took those measurements, and the first thing we did is use them to, we're interested in trying to get at how representative are these data for typical UTLS, even though we basically just measured in a small region. And so the only way we can really do that is to try to validate satellites or global models, and then use the model to tell us how much is in the rest of the world where we didn't measure. That's the best we can do. So that's what I'm showing here. And what we did was this on the left here. This shows this blue range, shows you the statistics from our aircraft measurements. And what we did was use Wacom and GEOS5 models using flight trackers. So we'd just sample the model along the flight tracks for the plane. And the comparison seemed really good. The model captures some of the high plumes that we saw, but outside these plumes also sees quite low values. And so these solid lines, this red and this green here, show these These models sampled along these are flight paths, but then the dashed ones over here show you what the model sees in a zonal average. So zonally average, it's lower than we saw. But the agreement along the flight tracks is pretty good. And then over here on the right, I'm showing a comparison between the zonal average from the models and the ACE-FTS satellite, which is on the left here, basically on top of our data, and these measurements from the Wacom satellite, which is over here. Thanks. Yeah, this is MePass data.
Wacom satellite's coming later.
Right, you guys are working on that.
We don't want that data.
Yeah, so, right, we're disowning this data. Anyways, yeah, so they basically, so they're, they have basically large error bars, which were published in this paper, where they published these data. And this is just one sigma I'm showing. So if you put 2 sigma on there, clearly it overlaps our measurements. But the average is obviously way outside the range that we measured. And that's problematic because this satellite is really the only data that was used to validate the one model that has been used as a reference point for the stratospheric aerosol budget. And so I'm talking about that here. So on this slide, I show, again, same profiles. This red one shows our measurements from the Guam mission. And then this blue, this is just the same data I showed you on the previous slide. And then I showed you a little bit of the Global Hawk data up here because that's where it is, and you could see something pretty similar, single PPT values. And the problem here is, so this orange line shows you the SO2 value that I showed on a previous slide, which is in the so-called AER model, and they have something like 30 or 35 PPT at the tropopause. And given that value, they calculate that SO2 is something like half of the stratospheric aerosol budget. Whereas if it's this low value, then it's playing a pretty minor role in stratospheric aerosol in these background volcanic conditions. So this is still, as far as I know, this hasn't, this paper was used as a reference for a recent Spark review paper. And this was the only model study that was cited in that paper. And so in that paper, it still says that SO2 is something like half of the background stratospheric aerosol budget. So it'd be nice if there were more papers saying otherwise. Okay, and so one important point, though, is that if SO2 isn't really playing this big of a role, then probably there are other species that are, this kind of leaves a gap in the aerosol budget potentially, which might be filled with organic material, which is not included in a lot of these models of stratospheric aerosol. So this is the point I'll come back to a little bit. Okay, and so, so that's, this idea that SO2 isn't, there's not a lot of SO2 tropopause that's going up there, and potentially there's more organic material that's playing a role in the lower stratosphere, is kind of supported by these measurements from PALM. So now I'm showing you a figure from a paper in 2014 that summarizes some of the measurements that were made using PALMs in Costa Rica. This is Dan Murphy's instrument that measures mass spectra of single particles. And this figure he does this analysis where he's looking at mass spectra of single particles and saying, sort of identifies 3 different types of particles in those mass spectra. Some of them are mixed organic and sulfate. Some of them are basically sulfuric acid, basically just sulfuric acid, and some of them are sulfuric acid mixed with meteoritic material. And what he shows here is that up to the tropopause, basically these organic sulfate particles are all the aerosol. And once you get up into the lower stratosphere, you see less of those and more just pure sulfuric acid particles. But these organics are important up for the first few kilometers at least into the stratosphere. And then this is a figure from this paper by Pengfei Yu in 2016. This is just a modeling study. And what he does there is try to attribute the chemical origin of all the aerosols in the stratosphere. So up here is blue is primary organic aerosol, and that's essentially just aerosol that came from it's POA in the troposphere, and then it gets transported into the stratosphere. This green is secondary organic aerosol, a lot of which is also just transported into the stratosphere. And then red is sulfate that's created from OCS photolysis. and black is the other sulfate. And so, yeah, so this is basically the younger layer. This stuff up here is due to the OCS, but there's a lot of aerosol down here, which is not related to OCS at all, which in one model could be a lot of organic material. Okay, so I'm going to switch gears here a little bit and just talk about some of these high SO2 events that we saw in some of these flights and where they came from. So here I'm showing a map of, these are all the flight tracks from our flights from Guam, and colored by SO2. And you can see there are a few different locations where we saw basically a bunch of SO2. And I've shown in the vertical profile over here, just colored, let's see, these three different colors are three different flights. And this cyan one is due to this large typhoon, and that brought some SO2 up quite high. This blue one here is due to a volcano that we sampled down here, and this green one here is due to this what appears to be a pollution plume from Asia that we saw. And right, so I'm interested in some of these high values. One of the reasons that we could be interested in these high values is due to nucleation of aerosols. So this is a figure from Chuck Brock's paper in '95. They just looked at basically very small aerosols in the upper troposphere and lower stratosphere, and showed that basically this region in the tropical UTLS, or in the tropical upper troposphere really, is where they see the highest concentrations of very fine aerosols, and this may be a really important region for nucleation of aerosols that are spread globally. And so what I've plotted here on the right, I just did a calculation where I calculate the nucleation rate of aerosols, just assuming binary homogeneous nucleation and using our measurements of SO2 in water and temperature. And you can see that the range of SO2 that we see from 1 to 100 ppt can create many orders of magnitude range in this nucleation rate. So you could think that in these plumes there could be a lot of aerosol nucleation that happens there. Okay, so where a few of these plumes came from that we can identify. This one flight we did, we flew basically straight south here near this volcano, and this is where we were intentionally going down there to hopefully sample a plume from this volcano. And these lines here show some back trajectories showing that the air we sampled along this region really came from this region. And then over here I'm showing a curtain plot. So this is 5 degrees south latitude, so at this end of the flight, and then 10 degrees north, so up here. And then the plane just did these profiles. And you can see this one is colored by SO2. And you can see we saw these nice layers of SO2 coming from the volcano. And we saw the same thing with the aerosol mass mixing ratio. You can see that there's some nice layers that coincide with the SO2. So that seems like a pretty clear case of, this is not a massive volcanic eruption. This is just SO2 erupting near the surface but being transported up into the UT by convection. And one of the things I've done is just sort of look at the tracers, well, some of the tracers that we have, and see if they make sense. So on the left here, I'm showing you we have measurements of CO, and these are GC measurements. So they're every few minutes we got a sample, and so I'm just kind of looking at these statistically for the flight compared to the typical measurements for the mission. And this black region shows just all the CO data for this whole mission in the region. And this red shows for this volcano flight. So it appears that if this was a pollution plume, instead of a volcano plume, you would think CO would be maybe higher than average, but indeed it's kind of low. So it's cleaner air. And then on the right here, I'm showing the ozone. And so ozone is this gray region, shows you the statistics for the ozone for the mission. And then overlaid are all the measurements from this volcano flight, colored by SO2. And ozone, basically, if it's a really recent convection, the ozone should be quite low because the air at the surface is pretty clean. And we don't really see anything like that, but we also don't see, it just looks like pretty typical air for the region. And this is not really the case for all these plumes that we saw. This other plume that we saw was when we flew just south of this Typhoon Hemi. And this is an image of the typhoon on the day we did this flight, and you could see that in the outflow here we're seeing some high SO2. And similar here we have these back trajectories show that basically all the data, these are back trajectories from where we measured it going back in time a few days and altitude. You can see that this is Eric Ray's analysis. It shows that most of this air really was just brought up through this typhoon quite recently. and really didn't come from anywhere that you'd expect to be polluted. And the CO and the ozone kind of agree with that idea. The CO, again, was pretty low on this flight, or in this region where we saw high SO2. And the ozone actually was really quite low. So you can see, it's a little bit hard to see, but the highest SO2 measurements that we had, these are all above 17 kilometers now. So really quite low ozone. So some of the lowest values we saw, this is like 20 ppb, or 30 ppb, and so much lower than normal. And this is kind of interesting, actually. So it's a lot of SO2, but it appears to not be from a volcano. Well, not be from that big volcano. One idea is, but anyways, it seems this area really has an origin near the ocean surface in this region, and so I'd be interested in people's ideas for what this was. One idea I have is that it's just a volcanic vent near the surface, possibly, or it could be a ship track. But yeah, so that's one plume, and then we had this other flight that I think is kind of interesting on this transit flight. We flew from Guam to Kwajalein, and we profiled up and down. On this flight, we didn't get quite as high, so the top of the flight track was about 16 kilometers. But it was interesting. We saw this big plume of SO2 here on this northern extent, and all these trajectories come back from the Asian continent. These are 10-day back trajectories. And the CO on this flight was sort of above average, which is suggesting that it's polluted air. But the thing that's possibly the most interesting here is the ozone seemed quite low. So I'm showing again here a few different things. This is the SO2 profiles through this plume. Here's SO2. And then I guess if you just look at the bottom, this shows the aerosol mass, and you can see there's also kind of elevated aerosol mass in that region also. And the water, it's a little bit hard to see, but these lowest values are something like 4 ppm, suggesting that this is really air that's been either through the tropopause or very near it. But the ozone here was really low, so it's these lowest values are something like 30 ppb. So yeah, I'm interested in people's ideas on what could be going on here. It's either the air really came from the surface and these back trajectories are wrong, and also the CO is lying, or I'm not sure. It's just these values are lower than you expect, I think, basically anywhere near the surface in Asia. And so I'm curious if it's possible chemical destruction of ozone in this plume. And then we saw one other clear pollution plume. This is on our flight back from Hawaii to California. At the end of the flight, we just descend, and we see kind of a plume here that comes back from Asia, and it's just something like 3 days, the back trajectories say, it took to get from there, and was air that came from the surface just a few days ago. Okay, so yeah, this is the last kind of event that I'll show here. All right, so here's some of the data from these global hawk flights we did last fall, and these flights might have been pretty boring. I mean, they still might be pretty boring because we basically just cruised in the lower stratosphere. But one thing that might make it interesting is it is in this time of year. This was in August, and this is kind of when the Asian monsoon is bringing a lot of material into the lower stratosphere. And so if you look at, over here on the right is an image from this GEOS 5 operational model, run in forecast mode at the time. And this is SO2 at 70 millibar, and the range is up to 100 ppt. These highest values are about 100 ppt. And so this model thinks that there's a lot of stuff being brought up here through the monsoon and transported all the way across the Atlantic and over into this region where we flew. And we really didn't see that. So this is a little bit complicated, I guess, but on the black here, I'm showing, this is the statistics from one of these flights. When we flew in this region at the time that this model is saying there might be 40 ppt of SO2, we see it at most about 5. And this is in comparison to, so this is during October 2016, that's when we were in Guam, and this red profile is what we saw in Guam. So you can see this model thinks that the Asian monsoon is quite important for bringing SO2 up into the lower stratosphere and spreading it globally. But we certainly saw nowhere near as much as that model sees. And this is really, I mean, I just showed one profile here, but it's really, we measured in this region for about 15 hours, and we did this on a few different flights, and then also one in California, and we really saw very similar measurements on all these flights. One thing that is a little bit interesting is we do see SO2 going up above the tropopause, which is something we've never really seen before. So I'm not sure if that means that this is some from Asian pollution, just not nearly as much as that model sees, or maybe all the SO2 here was removed by some other process. I'm not sure. All right, so yeah, this is my conclusion slide. All right, so we basically have now these 3 aircraft campaigns measuring SO2 in the UTLS, a lot of it in the tropics, and the typical values we see are about 5 ppt, and this is not enough to be very important for the stratospheric aerosol budget. And you know, it's, yeah, I mean, this may leave a gap in stratospheric aerosol budget in some of these. So there are a number of models, I mean, Mike's familiar with this, that basically try to only have sulfate and try to have a balanced budget for stratospheric aerosol with just sulfate, and I think that we know that's not really true. So organics may fill some of the gap in this budget. We have a bunch of measurements of high SO2 values sometimes, and it's clear that the convection can bring SO2 up into the upper troposphere. And so we saw this with these typhoons, and most of these plumes that we've seen have, well, we think it's not too hard to figure out where the SO2 came from, so it makes sense. So that's significant. But we're still not sure that these are really that important for bringing a lot up there to perturb the stratospheric budget in these background conditions. And yeah, this goes along with that. It's kind of interesting that we don't see nearly as much up in the lower stratosphere as is suggested by the GEOS5 model. So some things I'd like to do is sort of use some of these measurements that we have of SO2, of these high values, to test the convective removal of SO2 in these models, test the parameterizations for convective lofting or wet removal of SO2 in models. And I'd like to see if we can say anything about these measurements we have from last fall, and if it's really telling us anything about Asian pollution, transport, or maybe the model is just totally wrong for understood reasons. And then the next thing we're really doing is we're making this new instrument to go on this ATOM 4 campaign and do this flight here in a couple of months. And one of the goals there is to look at aerosol nucleation, but I think it should also help us, it should hopefully help us learn a little bit about convective removal of SO2 or lofting of SO2, because we'll get measurements down close to the surface, which we don't have at all at this point. So with that, I'll just take any questions people have.
So we typically use the microphone so anybody watching online can hear the question. So anyway, any questions?
Nice talk, Drew. Thanks for coming over to do this. So is anybody on ATOM doing aerosol composition?
Yeah, I mean, there's both POMs and there's an AMS also on there. I don't think there are any filters. And of course, this guy in the back, they measure black carbon, but you're probably not too interested in that. I don't know.
Yeah, it was just more for the organics. That's going to be really interesting.
Okay. Yeah. Yeah, it'd be nice. I mean, yeah, I actually haven't looked. I'm not sure what they've seen so far. But, you know, so they get up to 12 and a half kilometers. And I think that the AMS has difficulty, at low concentrations, AMS can't really quantify it. It's a bit challenging, I think, probably to just totally quantify how much organic aerosol is up there, but they get a lot of statistics, so yeah.
So Andrew, thanks very much for the introduction. That was very helpful.
Sure.
So regarding the SO2 in Asian monsoon outflow, I've been thinking a number of things. One is I know the recent StratClim campaign, the Geophysica did see a very high plume.
Yeah.
And so I guess the thinking is that there is a lot of SO2 in the Asian monsoon outflow. So the fact that you didn't see it, how much is the particular forecast run was not representing it right, or is it just a pure inhomogeneity in the space? So from that point of view, the MIPAS data, has there been strong seasonal cycle or spatial structure that potentially suggests that the time and the location of your measurement, to what extent is representative for budget? Or so I just wanted to comment on beyond the mean.
Yeah. Well, yeah. One thing. Obviously, I've heard just from you about the StratClim measurements, and I just heard this, the value that they measured, and I have no idea. I don't know if that was, they measured a really high value one time, or if that was typical. And so it's, like you said, spatial inhomogeneity may explain the difference. I'm not sure. Are you under the impression that they saw this? They saw 100 ppt everywhere, or they just...
Yeah, at the time, I think because just after the campaign, they probably just processed the final number, but both two flights had very high values.
Yeah.
Yeah.
So it'll be great to see when they make those data available or when they publish them, if they saw just a couple of values really high a couple of times, or if they see a lot everywhere. And that's nice because that occurred if this is the same time as they were flying, right? These measurements that we made.
So I guess I was really thinking from that point of view, should there be, I'm sure there will be opportunities to target more on the Asian monsoon outflow. That's really the...
It'd be great, yeah. Yeah, we'd like to. And then, but then to your question about, you're wondering how representative our values are. How well can we just compare directly to MIPAS due to...
Or is MIPAS suggests a very large seasonal cycle or spatial distribution that so will help you to design future flight in a certain region?
Yeah, I'm not sure. If we want to see, I think that we think at this point that, this error bar, MIPAS has both a precision and an accuracy problem with SO2. So, yeah, it would be nice to think that you could just not look at the absolute value of their data, but just go look for spatial structure. And I think my opinion is, at this point, we don't think you really can at these levels. Maybe above 100 ppt, you can do that. But at 20 or 30 ppt, I'm not sure that... Well, I don't think that there's evidence that suggests that you can. But we could... if it is... they should have a big... I should go look. I either did look at this... Well, I either looked at it with MIPAS or with ACE to see if there was a big signal over the Asian monsoon, and I don't recall seeing it. We should just go... That'd be the one place just to go look, right? See, do they see a value there that's similar to what was measured on the Geophysica? And if so, then we could try to use it other places to see where to go.
Thanks.
EPAS has been an outlier in some other quantities.
Yeah.
It has like a 6 kilometer vertical resolution, not much more than that.
Yeah. Yeah. Yeah, I think at this meeting we were just at last week, Mikhail Hofner, who did these retrievals, said, all right, I finally believe you that we're wrong. And he just says they have a difficulty with water vapor in the retrieval there, and it's, yeah.
Could I ask whose MIPAS that is?
Which retrieval?
Yeah, several retrievals, and they differ some of them differ quite a bit.
Yeah, I mean, these were published by, I mean, Mikhail Höfner was the first author on those retrievals. He's at KIT. And so I think those are, if you go to the KIT website and try to get them, that's what you get. Yeah. So I don't know, do you think that there are some other retrievals that have showed much lower values? It'd be interesting to know. But
I'm not sure. I haven't looked at the SO2.
yeah. Yeah.
Any more questions? I had one question. On some of your long flights, like especially on the Global Hawk, where you're showing some variability, let's say on a transit flight, and I might be naive in asking us, but is there some sort of diurnal variability that you could be putting on top of the spatial variability?
I mean, so the lifetime is a few, it's a week or two, or people put these, anyways, the photochemical lifetime, I don't think is enough to provide you, say, a diurnal cycle. Just, let's say you had a constant source everywhere. I don't think you'd see diurnal variations due to OH. And I'm not sure, so I'm not sure there are other reasons that you would either.
Yes, there was one plot that you also included ozone along with it, so I was wondering if that could play a role, nighttime versus daytime.
Yeah, I mean, if there's a diurnal variation in some of the intensity or frequency of convection, I suppose it's possible there could be something. It'd be interesting to know. I'm not,
It's just curiosity more than anything else.
Yeah.
Okay, well, let's thank Andrew again.